So in this video, we're going to go over how to balance a chemical equation. So balancing chemical equations is not particularly fun. It's somewhat of a tedious process, although there are some of you out there that might enjoy it. Just look at it as kind of a game, sort of stretching your brain. Do a bunch of these. When you figure out how you're supposed to balance a chemical equation, that's great, but it's not really a substitute for practicing it. So chemistry, just like math, is not a spectator sport. You need to practice it so that you can perform, say on a test, quiz, or whatever. Makes your homework go faster too. So here are the rules. They're not so much rules as they are guidelines. Well, the first one is definitely a rule, but the second one just bolsters the first. So the only thing you can do is you can adjust the coefficients. So let me think of, well, we'll use the first example down here as an example. So these are going to have different coefficients here, here, and here. So x, y, and z are the coefficients. They can be integers. They cannot be half or quarter or third integers. So you can actually use non-integers, basically fractions, as part of a strategy or a method of arriving at the correct balanced chemical equation. So conservation of mass, that is just a different way of saying the first one. You can only use the coefficients to make everything balanced. Do not add anything to the chemical equation, provided the chemical equation is correct. And for you guys, you need to assume it's correct, unless your chemical intuition tells you otherwise, and there's a typo or something. That's the only case I can think of. So, as far as our strategy is concerned, count the atoms, and I'll show you how I organize it. You can come up with your own method. So you count the atoms on both sides, and you compare it. You see what needs to be adjusted. Use the coefficients to balance non-hydrogen and non-oxygen atoms molecules first, if possible. Then balance hydrogen and then oxygen last. This is always a good idea. Check your work. Not necessarily required if you are confident that you got it, but it's highly recommended. So here we have our first chemical equation. It's iron reacting with oxygen. Presumably there's the input of heat to get the reaction to go. And then it forms its ferrous or ferric oxide, which is this right here. So we need to come up with X, Y, and Z to balance the number of atoms on both sides. So what I do, and actually I have the balancing notation down here. Usually I do it like this, and I have another shorthanded which I will probably show you at some point. But so count up the atoms on both sides. We have one iron over here. I'm not going to always show one, but one iron there, two oxygens, then two irons on the right, and three oxygens on the right. Okay, so what could we put in X, Y, or Z to further balance the equation? Well, we're going to start with non-hydrogen or oxygen atoms. So, of course, that is iron. There's nothing else. So what we're going to do here, since there's only one iron on this side, we'll just put a 2 right here, right? And then this is very thorough and for teaching purposes primarily. But I find that when you guys start doing these, you're not going to write out everything so many times, but this helps. And first time I filmed this video, there were problems with my video recorder. It was doing automatic zoom, which was awful. But I found that writing most of the stuff out and then talking to you and just adding stuff should be more clear for you guys, and certainly the length of the video will go down. So let's go ahead and take an audit of how many atoms there are on both sides. So now we have 2 irons on that side. Again, still 2 here. 2 oxygens on the left, and then we have 3 here. So as I mentioned before, we can only use integers for the coefficients. However, as an intermediate step, it's sometimes useful to use fractions. So let's stick with the coefficients that we've already had, or we've already added. So we have 2 here, and this oxygen, so up here, let's change colors again. This oxygen on the left, there are 2 on the left and 3 on the right. So to just brute force make the number of oxygens on the left agree with the ones on the right, we can add 3 halves or 1.5. I'll do 3 halves because we're going to use fractions later, but 3 halves is the same as 1.5. So if we look again, if we go and count atoms again, we've got 2 irons, 3 oxygens, 2 irons, 3 oxygens. So everything agrees. However, this is not allowed, right? So what we need to do is multiply it by something so that it equals, all the coefficients equal an integer, and that's quite straightforward. So what we're going to do instead of, manually add stuff, we're just going to, I guess we are manually adding additional things. You just multiply all this by 2. And so we get, let's check my work. Yep, this is right. 4 irons, 2 times 3 halves is 3 oxygens. And then that is multiplied by 2. So that is our answer. I'm not going to check all of these. I'll check this one for you guys. 4 on that side, 4 on this side. 6 here, and 6 here. It checks out. Exciting stuff, right? Okay, so next, this is an interesting and very important reaction since the Industrial Revolution, or afterwards, when the technology got to the point where it was a feasible and profitable reaction. For the demands, the agricultural demands of the globe, we need more fertilizer, and it was hard to go, grow basically, or use plants and naturally occurring resources to get fertilizer. And so this guy, it's Haber, and I forget the other guy's name, came up with this process right here. And it's a fairly straightforward reaction, and the reagents, the reactants, are fairly plentiful or can be made easily. So one of them is nitrogen, the other is hydrogen. This is molecular nitrogen, molecular hydrogen, and it forms ammonia, which can be later put in something else, fixated, and we have what's called fixated nitrogen, which plants can use, and it's essential for them to grow. So if we're trying to grow a lot of plants, more plants than a typical tract of land can support, we need additional fertilizer. So the Haber process is, the conditions are pretty wild. So 200 atmospheres, so that's 200 times the pressure that you're feeling right now in South Carolina. at sea level. That would be uncomfortable. And it's at 400 to 450 degrees Celsius. And I've seen temperatures that are higher than that. So these are huge reactors that are reinforced, and you have gases streaming in, reacting. And as you can see here, it's in equilibrium, which means it doesn't go to completion. There's actually a distribution of these three species, and they have a way of extracting the ammonia. So that's enough of a aside. We're just here to balance chemical equations, right? Well, sometimes I find if you know a little bit about the background of some reactions, you're more likely to remember them. And this is certainly one of the most important ones in modern day society. All right, so let's count atoms. So we have 2 nitrogens and 2 hydrogens on the left. We have 1 nitrogen on the right and 3 hydrogens on the right. So let's see, what do we want to balance first? Well, there's nitrogen and hydrogen, and we're supposed to start with non-oxygen or hydrogen ones. So we will make the nitrogens agree. So I'm going to go ahead and put a 2 here, and then we'll take another count. So 2 here. As I said, this is tedious. 2, and then unfortunately we now have 6 hydrogens. Well, it's fortunate that we have a molecule involved in this reaction that is just pure hydrogen by itself. So if we change the number of hydrogens in that, it's not going to affect anything else in the equation. So we just simply add a term there that makes this number agree with this number. So we're changing this one, right? So what's our new equation look like? So we already have the 2 here. We need 6 on the left, so we just add a 3 here. And that, my friends, is a balanced Haber process chemical equation. All right. Oh yes, combustion reactions. So to keep it simple, we're going to use straight chain hydrocarbons. Straight chain hydrocarbons. Well, methane is just the simplest one, but ethane can't help but be straight chain. Propane is like that. Butane is like that. And I'm an organic chemist, so I use the shorthand notation. So this is the equivalent of CH3, 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 CH2. I know that looks weird. CH3 and so on. So C, 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 C. So for hydrocarbons, it's just carbon and hydrogen. The generic formula for the straight chain, well, the general formula is CXHY, some number of C's of carbons and some number of hydrogens. And in a combustion reaction, they are exposed to heat, and it doesn't take much heat, and it sets on fire, and it generates more heat, so it gets even hotter, and it sets the other hydrocarbons on fire. So it's very exothermic. But we have a hydrocarbon here, oxygen, and the products are carbon dioxide, which is not great for the environment. Too much is not great. And water, which is benign, I guess. If anything, beneficial. We can always use more water. All right, so starting with the simplest hydrocarbon, methane, CH4. In the presence of oxygen, we make CO2 and water. All right, so let's take an audit real fast. I don't know why I call it audit. So how many carbons do we have? We have 1 carbon, 2 oxygens on the left, 1 carbon on the right. Oh, forgive me. I ignored hydrogen. And actually, let's keep them. No, we'll keep them as the ampere. So, 2 oxygens, 4 hydrogens. I meant to add hydrogen later, and then I skipped over it. All right, so on the right we have 1 carbon, 3 oxygens, and 2 hydrogens. Okay, so what we need to do is these are, the carbons are good, at least for now. The hydrogens and the oxygens don't agree with each other. So, since carbon is taken care of, let's start with hydrogen, as prescribed by our strategy that we talked about earlier. Okay, so looking at this one already drawn out for us, we have 4 over here and 2 over here. Well, that's easy. We can just simply add 2 here. So let's take another look at what that results in. I'm going to do an intermediate sort of count of the atoms. So methane on, why is my thing doing that? So now we have still 1 carbon, 2 oxygens, 4 hydrogens, and what? 1 carbon, 2 oxygens. Oh my gosh, I screwed that last little part up. So 2, we get 2 from here, and we already have 2 here. So we have now 4 oxygens, right? And how many hydrogens? 4 hydrogens, which is what we were going after to balance in the first place. All right. So how would we continue to balance this? All right. Well, we have what doesn't agree now? The oxygens. So let's go ahead and put in the coefficients that we do have. We have a 2 here. And the number of oxygens, since we have 4 on this side, and oxygen is by itself. Again, that makes it easier. We just add 2 here. And so this is the final balanced chemical equation. And you can see, unlike up above, let me scroll up for a second, sort of spelled it out for you guys. This was 2 steps, right? I added this and then this and sort of separated them. But so I ended up writing the chemical equation out 3 times, even though it's 2 steps. Here, making it a little faster, just writing it out twice and adding the second step to first step to the unbalanced, second step to the partially balanced, and then making it into the final balanced one, if that makes any sense. For propane, a little bit more complicated. Let's see. Yeah, we got this one right here. All right, what color should I use? Darn it, I didn't take an audit, or I didn't count this one. So I'll do this one quickly. Propane combusts just like any other hydrocarbon. This one has 3 carbons, 8 H's, 2 oxygens on the left, 1 carbon. I like to keep the H's and the oxygens in the same order on both sides, even if they don't appear that way. Then we have 2 hydrogens, and how many oxygens? 3 oxygens. Okay, so what we want to do is we are going to balance the carbons first, right? because we always start with non-hydrogen and oxygen atoms. Well, it turns out everything is mismatched. Nothing is the same amount on any of the sides. Either of the sides. Okay, so sticking with this sort of pleasant orange, we'll just put a 3 right here. Okay, and then I'm going to take my second count here, which is, a little redundant since you guys know. And on a test, and when you do enough of these, you don't have to write it out each time, and it's sort of a pain. 3 C's, 2 H's, and now we have 6, 7 oxygens. Well, it's too many oxygens, not enough hydrogens on the right. Correct? So what we're going to do is we're going to balance the hydrogens first and see where that gets us. I don't know why I have that 1 there. Could have left it probably. I don't know if it was distracting or not. Okay. So, what's our count? 2 over here on the right, 8 over here. So what we can do is 4, and that balances everything, right? However, put something slightly off, right? 2 oxygens, how many carbons over here? 3 hydrogens. We now have, well, that's convenient. 8. But we have, let's see, 3, 6. We have 10 oxygens over here. Well, that's actually simple to solve, right? So we're looking at the number of oxygens on this side versus over here. So 10 versus 2. Well, all we have to do here is put a 5, and we get our balanced equation. Okay, those are the specific examples I wanted to show you. Now, for those of you that are interested, if you see a hydrocarbon and you have a good memory and you maybe not enjoy memorizing stuff, but it's not too much of a problem for you, there is a simple equation. So if you remember back, this is our generic or general hydrocarbon combustion, it's not balance, equation, right? Well, depending on your hydrocarbon, like propane was what? It was C3H8, right? It's propane. Butane would be C4H10, C5 this is going to be pentane, let's see, 12. Yeah, it just goes up by 2. So the formula for hydrocarbons, at least straight chain ones that are totally saturated, is CnH2n plus 2 is the number there. Not a very difficult equation to memorize. Down here, this, if you choose to memorize it, it could save you some time on a test if there's a long chain, a complicated hydrocarbon combustion reaction that you have to balance. You take the subscripts of the hydrocarbon and you put them in their designated places. So there's another place here, so just 4 places. And if we take the example of butane, X is equal to 4, Y is equal to 10. So you plug everything in. These are all the numbers and where they go. This is the simplified one. Simplified. And what happens is we get this equation right here, and of course we can't have half integers in our final balanced equation, so we multiply it by 2 and we get this balanced equation reasonably quickly for butane. That's it. That's all I have for you, at least today, on balanced equations. Read the chapter, look at this video, other videos, and do the problems. This is one of those where it just, comprehension is not enough. If you've made it to the end of this video, it's important to know that you need to practice these. Now, don't spend all of your time balancing equations, but get to a point where when you see something totally new, or 5 to 10, you can just rip through them with a fair amount of confidence, and then after checking your answer, be like, well, I got the last 5 right. Like, this feels pretty good. I think I've got a handle on this. So that's it for today. Thanks for your attention.